Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about the law of sines and the law of cosines today. Little bit of review. Remember, we have right triangle trigonometry with kind of the abbreviation SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Of course, tangent then can be thought of as sine over cosine, and we have our right triangle, and then this allows us to find different values of sine and cosine based on the angles. You can check out the previous Thursday tidbit. I'm linking below if you want to check out and review that a little bit more. It's not really the big focus of today. We are going to use some trig things. I also want to just briefly mention, because we might have, or we can have angles bigger than 90 degrees in terms of trigonometry and in terms of triangles. So, right, how do we extend these definitions of sine and cosine? And then tangent can be thought of as sine divided by cosine. Well, we can do this with a unit circle. So we kind of extend this and we think of our hypotenuse as 1. And so that hypotenuse then can be anywhere on this unit circle. And then we can think of the sine and cosine values as the kind of x and y coordinates of those points. So right, then this kind of x value here would be giving us the cosine of theta for this angle here that would be bigger than 90 degrees. And then, of course, sine of theta could be thought of as the y value. So kind of without too much imagination even, you can kind of see how these things relate to our right triangles. We have two right triangles drawn here. Pick whichever one you want. And you have kind of the x value and the y value, and things work out very, very similar that way. Just wanted to mention that because, right, you could do then sine of 100 degrees or sine of 120 degrees. And these can show up in general triangles, which is really what we're going to be focused on today. So, what do sine and cosine tell us then about general triangles where we don't necessarily have a right angle? Right, so we have kind of the first of our ideas is the law of sines. So let's just put that on pause a second here, but I just want to kind of say quickly what I mean again by a general triangle. So I have an acute triangle drawn here, but this still would all hold if we had an obtuse triangle. We have the three angles and the three vertices, right? So we have kind of angle A, angle B, and angle C. So we have kind of three different angles in this triangle there. And then because of the law of sines, and then because of some other relationships between these things, the common way of labeling the sides A, B, C in terms of lengths are again with our opposites. So if we have our three sides of this triangle, we call kind of side BC, we call that little a in length, because that is opposite from the A side there. Right, and then for the B, opposite of the B, we have side AC with length little b, and opposite of side C, we have length little c with where that is the segment AB there. So that's kind of the general way we kind of think about these things and think about these kind of angles and lengths in a triangle. So in a triangle like this, right, so in a triangle with sides A, B, and C, and then opposite angles, angle A, angle B, and angle C, we have this relationship with ratios of sine of angles divided by a corresponding side length. So sine of angle A divided by length A is sine of angle B divided by length B is sine of angle C divided by length C. So we have a lot of symmetry here, right? And all three of these quantities are always equal to each other. So in any triangle, this happens there. So let's take a quick look at a proof idea. And this really shows that a lot of the stuff you do with right triangles has kind of natural extensions to what you're doing with kind of general triangles and things like that as well. So why is this a proof idea? We're going to kind of do it for this type of triangle. It's going to be, we're going to prove one of the equalities, but these ideas really work in general. And based on what I just said, it shouldn't surprise us that our kind of first step is to turn this into a couple right triangles. So from C, we're going to drop the altitude, and let's say this altitude has a length of h there. Well, now we have some right triangles, and we have h is the opposite of A here, and it's also the opposite of B here. So using basic right triangle SOHCAHTOA trig, right, what do we have here? Right, we have sine of angle A is opposite, so the opposite here is h, divided by the hypotenuse, which in this case is B. So sine of angle A is h over B. And we have a similar thing for sine of angle B. Right? Sine of angle B is h over A in this scenario there. So, right, moving things around a little bit here, right? So this tells us then that h, right, we can solve both of these for h. So h is b times sine of angle A. And you probably can see where this is going by now, right? Because then we also have h is A times sine of angle B. And so then if we set these equal to each other, right, we have to have that b sine of angle A is equal to A times sine of angle B, right? So since those two things are also equal to each other here, we can rearrange to get our law of sines, right? So if we divide by b, we have sine of angle A, and then the b goes to the other side, we can divide by A on both sides. So sine of angle A divided by A is sine of angle B divided by B. And so, like I said, officially speaking, right, we've proven one of the equalities we need for the law of sines, but this gives you the general idea. The same things work in kind of other cases, and there's a couple of little weird things that might go on if you have an obtuse triangle, etc. But this gives you the basic idea, the basic thought process for kind of coming up with proving the law of sines. Now, we'll do some examples, or one example / application at the end, but let's jump into the law of cosines here too. So the law of cosines is, again, the same triangle. So in a triangle with sides A, B, and C, and angles, angle A, angle B, angle C in this case, we have kind of a bunch of relationships involving cosine and the side lengths there. Now, let me just highlight one of these, right? Because they're all kind of just rearrangements of the other. And when we look at this, it should remind us a lot of the Pythagorean theorem. In fact, this is an extension of the Pythagorean theorem, right? Because if you think about the unit circle definition a little bit, if we have a 90-degree angle, cosine of 90 degrees is 0. And so this just becomes the Pythagorean theorem when you have a right triangle in this case. But in this kind of particular one, right, we have angle C over here. We have the opposite side C then in that case. And then it becomes an equation that's very, very similar to our Pythagorean theorem. The two other side lengths squared. So in this case then we have, right, b squared and a squared, and then minus 2ab cosine of that angle. So because it's not a right triangle, because it's not a 90-degree angle, we have a little bit of extra term there, this minus 2ab cosine c, that we'll need to use in some calculations from there. And typically you'll use this when you kind of want to find the c value, right? The reason I'm writing out 3 different equations here is that you typically use this for kind of a missing value of c or c squared. So if you know that other information, you can use the law of cosines to find that missing side length in this case. Okay, let's jump into an example of this. And this is what's sometimes called solving a triangle, right? You might need a calculator to do this fully because some of the trig values might not be nice or things like that. But a lot of times the law of sines and cosines, you can mix and match or use one or the other depending on whichever you prefer or what you find is easier to kind of go about finding all of the missing information or some of the missing information in a triangle here. So in this case, we have a triangle. It has 2 sides of 5 and 2 square root of 3. We have a 30-degree angle. And in this first portion of the problem, we want to find the missing side length AB. So we want to find AB, right, which I'm going to call the little c in this case there, right, because it's opposite that angle C in this case. Just as a kind of quick review of everything, right, let me write out the law of cosines, right? So we have one missing length, and I just kind of said when you have this missing length, this is oftentimes a good place to kind of use the law of cosines there. All right, so let me just write it out in terms of all of the variables first. So we have our c squared, right, is a squared, just what we had on the previous slide, plus b squared, minus 2ab cosine of angle C in this case. So this is our law of cosines, and it's going to allow us to find for that missing side length here. Now let's start summarizing our kind of information that the problem tells us as well. So, right, we have our 2 side lengths. Remember, little a is across from the angle A, so this is 2 square root of 3. Little b is across from our angle B, so this is 5. And we also know that angle C, so the big C in this case, is 30 degrees. Now, more importantly, let's review that kind of right triangle trigonometry a little bit. What is cosine of angle C? So we've kind of set up this problem so that the kind of angles and stuff, or this angle is not so bad. And remember, cosine of C, you can think of our kind of 30, 60, 90 triangle in this case. Cosine of 30 degrees is going to be square root 3 over 2 in this case. And so now we can kind of plug all of our values in to find C. So a squared, let's kind of just do this simplifying a little bit along the way. So 2 square root of 3, 2 squared is 4, square root 3 squared is 3, so this is 12. And then 5 squared is, of course, 25. And then we have minus 2 times 2 square root of 3. That looks a little bit annoying, but it looks a little less annoying in a second because we have times square root of 3 over 2 in this case there. So basically what we're going to have here then is 12 plus 25 is 37. And then we have minus, so the 2 and the over 2 cancel. Then we have 2 square root of 3 times square root of 3. So that gives us a 3 times 2 is 6 times 5 is 30. So this then is going to be 37 minus 30. And so we have 7 in this case. Don't forget, right, what we're kind of looking for. We're looking for our AB, right, which is the square root of this. So just kind of summarizing a final answer here, we would have AB is square root of 7 in this case. This is our kind of actual final missing side of this triangle. So kind of the name solving this triangle comes from, okay, you have the information, right? And we're looking for some of the missing side lengths or maybe missing angles, information about the missing angles, etc. Okay, let's do one quick final example with this triangle as well. Now, let's say we want to find sine of angle A. So just what we did in the previous problem, we know that AB is square root of 7. And we want to find sine of angle A. If you had a calculator, you could use what sine of angle A was to calculate, of course, what the angle was. But just in terms of an exact value, what we can do without a calculator, we can use the law of sines to find out what sine of angle A is going to be in this case. Right? We can use, of course, the law of sines then in this case. So the law of sines says sine of angle A, right, divided by A, well, that is equal to sine of angle B divided by B. So just thinking a second though, do we know anything about angle B? No. So let me just write this as then, this is equal to sine of angle C divided by C in this case. All right, so that's kind of what we have then for this setup there. Do we know what sine of angle A is? Nope, that's what we're looking for. So we have sine of angle A divided by A. That we do know. That is 2 square root of 3. And now we can start to see why we did this problem second. Right, now we have sine of 30 degrees. So sine of angle C is 30 degrees. And we can divide this but now by the side we just found, square root of 7 in this case. So what is sine of 30 degrees? Let me do kind of a couple of steps here quick. So sine of angle A, let's just move everything to one side. If I multiply by 2 square root of 3, we have 2 square root of 3 in that case. And then, right, we have times, what is sine of 30 degrees? Sine of 30 degrees is a half. So we have times a half. And then don't forget that we have this whole thing divided by 7 in this case. So after the 2's cancel, we get square root of 3 over square root of 7. And then if we want to write this in simplest radical form, we can multiply by square root of 7 on the top and bottom. And we have radical or square root of 21 divided by 7 in this case there. So it's not as nice of an answer. This isn't one of our special angles that I expect you to know, oh, sine of angle A is square root of 21 over 7, so our angle is blank, right? This is not a nice number. If you had a calculator, you could get approximately what angle A was here. But for now, let's just kind of keep it as we know that sine in this case. And you could use that in other calculations. A lot of the time, you don't actually need the angle. It's enough to know what sine of the angle is, or cosine of the angle is, etc. So hopefully these examples of solving a triangle were good today. Check back each week for a new Thursday tidbit. If you want to check out with more practice, you can visit ziml.areteem.org. There's a lot of good resources there, daily problems, monthly contests, all kinds of good things there. Otherwise, please like this video and subscribe to our channel if you enjoyed this. It really helps out. Otherwise, I will see everybody next week. Goodbye.